Here's where mathematics delivers its first surprise. Alice arrives with $10,000 but takes a completely different approach. She's going to bet just $1 on red, over and over again, until one of two things happens. Either she's up exactly $100 or she loses everything. This might seem like a much safer strategy. After all, she has 10,000 chances to slowly build up her winnings. She only needs to accumulate 100 more wins than losses before her bankroll disappears entirely. With nearly a 47.4% chance of winning each individual spin, surely her odds are much better than Bob's, right? Now meet Carlos, the richest person in our hypothetical universe. He walks in with $100 trillion, more money than exists in the real world. Like Alice, he's going to bet $1 at a time on red until he either wins $100 or loses everything. With such an enormous bankroll, Carlos has virtually unlimited opportunities to recover from losses. He needs 100 more wins than losses before accumulating 100 trillion more losses than wins. Intuitively, his chances of success should be astronomically higher than Alice's, shouldn't they? Here's where mathematics delivers its first surprise. Alice has only a 0.00265% chance of winning $100. That's not a typo. It's about 26 chances in a million. Despite her $10,000 bankroll and conservative approach, it's almost certain she'll lose everything before making her modest profit. But the real shock comes with Carlos. Despite his $100 trillion bankroll, literally a million times larger than Alice's, his probability of success is essentially identical, 0.00265%. The difference between their odds is so minuscule that you need a high-precision calculator just to detect it. For all practical purposes, the person with $10,000 and the person with $100 trillion have exactly the same chance of winning $100 using this strategy. The reason Carlos's massive bankroll barely helps him lies in the fundamental mathematics of biased random walks. In roulette, you're slightly more likely to lose each spin than win. Over time, this small bias compounds exponentially. Think of it this way. Imagine you're walking along a path where each step has a 47.4% chance of moving you forward and a 52.6% chance of moving you backward. Even if you start very far from the cliff behind you, the backward bias means you'll almost certainly eventually reach that cliff, no matter how far away it initially seemed. The mathematical term for this is certain ruin. When the odds are against you, even slightly, and you play indefinitely, mathematical certainty dictates that you will eventually lose everything, regardless of your starting position.